Take a look at this beautiful picture of the European Southern Observatory. There's a telescope at night quietly taking some of the highest quality pictures of the universe in human history. But when you look at it, one question might come to mind, which is, why on earth is it firing lasers? Before I answer this, I suppose I want to ask a second, also interesting question. Here's an image of the Hubble Space Telescope, but why did we send a telescope to space? What's the advantage of going into space? And that's the atmosphere. The Earth's atmosphere does admittedly allow humanity to exist. However, astronomers are perhaps not so keen on it. When light from a distant star passes through the Earth's atmosphere, it interacts with particles in that atmosphere. Remember, space is very close to a vacuum, there's not much there. But now it's going through an atmosphere. And that changes the light in many interesting ways. This then distorts the image a telescope would pick up, making it harder to see interesting things, making it harder to distinguish features of an astronomical object. So there's another reason to go to space, to get away from the Earth's atmosphere. However, this has some costs, one of which being the cost. Getting things into space is incredibly expensive. Just the weight limit alone makes getting into space expensive. And limits, of course, the size and quality of your telescope because of that limit. But you also have to build your telescope to handle the difficulties of space. And it's very hard to fix it or maintain it once it's up there. So what's the next best thing we can do? Well, we can try to improve ground-based telescopes to compensate for the effects of atmosphere. What would be really nice is to take that distorted wavefront received by a telescope and recover as best we can what it would have looked like before the atmosphere distorted it. To do this, we could make a mirror in our telescope out of smaller movable pieces powered by little motors or actuators. Link them up to a computer, and we should be able to change the shape of the mirror on a timescale of milliseconds. We can use an array of small lenses, which in the business is known as a Shack-Hartman sensor, to approximate the shape of the wavefront on the telescope. A wavefront being a surface containing points affected in the same way by a wave at a given time. The more physics-based definition being it's the points characterised as positions where the wave is in identical phase. Once we've approximated this shape, we can then adjust the mirrors in the telescope to correct for this. There's a problem, however. You can only correct once you know how to adjust the mirrors, and for that you need to know how the atmosphere is affecting your signal. You could use a naturally bright star from this, perhaps one we've observed from space, to get a well-known light signal. However, this is not ideal. You might not have a bright star in the area of the sky you want to study. And this brings us on to using lasers. Lasers are fantastic. They can emit a coherent signal with a lot of power behind it, well-known main wavelength, bandwidth and shape. They can emit this signal for a long way. So, this leads us to a couple of ways to work out what the atmosphere is doing to our light. Firstly, you could fire a laser into the atmosphere, so the laser light reflects off the atmosphere and comes back down to the mirror. This is known as the Rayleigh beacon method. It's wonderful, and it's fairly simple to implement. However, the reflection happens in the lower atmosphere, so it's not as good as it could be. Another interesting solution is called the sodium beacon. There's a part of the atmosphere called the mesosphere, which has many sodium atoms in it. tune the laser's frequency so that light gets absorbed by sodium in the atmosphere. Sodium then re-emits light. This allows you to measure your reflected signal from higher up in the atmosphere. You know the properties of the signal you've sent, and you've now seen how travelling through the atmosphere affected those signals. And you can use this knowledge to correct your telescope for the effects of the atmosphere. So in summary, the reason that telescope was firing a laser is to work out the effect the atmosphere has on incoming light from space. This allows us to compensate for that using mirrors in the telescope, giving us pictures on the ground with a quality incredibly close to that from a space-based telescope, and for a fraction of the cost of sending equipment into space.